Fair enough.
So, with no further ado, I present you Jarek.
Thank you. Woo! Okay, guys. Absolutely lovely to have you all on my another presentation regarding artificial intelligence and stuff. Once again, my name is Jarosław Hryszko, and well, I am known for the fact that mostly I work for a different artificial intelligence applications in an area of quality assurance, especially in such area which is called defect prediction. But today I will not tell you about the basic of the defect prediction, how to use artificial intelligence to predict defect-prone areas in software, because there are plenty of different presentations by my humble person available online. So if some of you, maybe most of you, don't know any of those presentations, you are more than welcome to go to the YouTube, for example, and search for example, my presentation from the Testwarez, whatever, 2015, where thanks to that guy with laptop, Maciej, I had this pleasure to present idea of the defect prediction for the first time. So, yeah, and also there is a recording. Thank you, my lovely wife. There is a recording because this particular video is in Polish, but there is a one presentation from this year's TestCon in Moscow, when I also speak about the defect prediction and basics of the defect prediction in my rusty English. Nevertheless, today will be not about the basics of the defect prediction. So once again, if anyone is interested in that, there are plenty of different material available online. Also, I will not present you any special use cases or business cases regarding defect prediction, because was also, those topics were also described by my humble person during different conferences, as well as in different publications. And also, this particular presentation will not be a very fancy one with some spectacular and glossy things, but with no useful content inside. Instead, there will be a lot of different and maybe sometimes a little bit complicated schemes. Also, I have this ambition to pass to you this very short and simple recipe how to use artificial intelligence, how to fully automate this usage of artificial intelligence to predict defect-prone areas in the software you test or you maintain or you develop, whatever, during this very short presentation. And also I need to restart my timer of the presentation. And I heard that some time ago, I heard that the most hardcore technical presentations should be written in a tech language, not presented in a PowerPoint. But I decided that writing a presentation for our conference in tech or LaTeX doesn't matter. It's too hardcore, so I decided to do it in LibreOffice, just because. Okay, but first of all, let's just let me remind you this difference you all for sure know, the difference between bug and the defect, to explain you, to remind you once again, what the AI-driven defect prediction is. So maybe only for the sake of this presentation, for the purpose of this presentation, let's just think that bug is just a mistake in a source code, human mistake, lack of semicolon, I don't know, bracket, something like that. But at the same time, defect, it's something with which the end user is not pleased with. So the discrepancy between users' expectations, between users' requirements, and the actual appearance, actual behavior of the application. That's a defect. Yes. Because sometimes you can have 100% bug-free code, but still it can contains defects. Because sometimes, for example, requirements can be wrongly written, for example. So developer can write a code absolutely correct, but still we can have defects in a software. And opposite, we can have some bugs, we can have some mistakes in the code, but still customer can be 100% pleased with the appearance of the software, with the software itself. Together with Maciej here, we had such case in our common past in one of the corporations we used to work together, that Maciej found a kind of critical or spectacular bug in one of the software we were testing, and we of course we escalated this fact, but the customer's answer was such that it's okay, because this particular bug well, it causes this situation when this software looks much better than without the bug. So we are pleased with the fact that this bug exists in the source code. So that's the difference between bug, mistake in the code, and this discrepancy between the actual appearance of the software and users' expectation. Luckily for me, we are not talking here about the well, formal definitions from the ISTQB. So once again, for the sake of this presentation and for the sake of this fact, then in the scientific world, we have defect prediction, not issue prediction, mistake prediction, or something like that. We have defects prediction or defect prediction, and the defect is understood in such way that this is this discrepancy. So we have this common well-known term, defect prediction, and in this particular application, let's say, defect is this discrepancy, but only there. Yeah. So that's why we have this defect prediction. And this is actually the answer for the first question some of you will have after this presentation. Why we need this artificial intelligence and machine learning to look for defect-prone areas, while we can use a static analysis of the source code. So if we go back to those definitions, it is clear that static analysis can be used for finding bugs, issues in the source code, different issues, but artificial intelligence is able today to predict defects, to predict facts that user will not be pleased with the actual behavior or looks of our software or interface. for the sake of this presentation, not just forget about those definitions if you are going to, I don't know, pass some ESTQB exams or something like that. Okay, guys, so this is defect prediction. And if we add to defect prediction fact that well known also to all of you, that quality assurance costs will grow with the every next level or phase of the software development process, it is quite obvious that defect prediction, apart from the fact that it is, well, obviously useful for that we as a testers will know where all those defects should be and where we should put a special attention, special focus, maybe put some additional test cases, some prioritization. Apart from that, if we start as early as possible, then we will save a lot of money, a lot of quality assurance budget, thanks to this simple Boehm law. Yeah, and well, on 2012, when I started well, my personal research together with my research team from one of the universities, well, we started with this idea that we need to make this machine learning stuff, this all artificial intelligence stuff, as easy as possible, because well, this you know, this c'est la vie. We don't, as a software testers or software developers, we don't really have time to spend on, I don't know, learning new language or implementing new techniques to have machine learning implemented. So I decided, or we decided together with my friends from the research team to use a NIME platform. Also, if you were participating in a workshop on the Quality Excites this year, or 2 years ago on the workshop during Testwarez, we also had this maybe pleasure to work with NIME, because we thought in my research team that NIME is a very easy to learn and easy to use tool to use this machine learning, to use artificial intelligence to predict defect-prone areas. The only thing which tester or developer needs to do is to put some such colorful bricks or blocks together. It takes just a few hours. Also adding all the stuff connected to gathering data for those bricks, and that's, to be honest, everything. And at the end of those data workflows, we will have prediction for our new software. And also this tool, as we can rearrange those bricks. If we use this tool, we can easily adjust what we already have to a changing conditions in our companies. So, for example, if we already have working defect prediction in a Java project, by just switching one brick, we can change the entire software defect prediction process to be used in a COBOL-based project, for example. And of course, after that, after we thought that using NIME and NIME extension, which we called DPRES, which stands for Defect Prediction for Software Systems, I have no idea why the second S disappeared. We thought that it is a very good idea, because it takes just a little time to implement this tool, to use this tool. But also, my humble person, I also prepared the entire defect prediction quality assurance methodology. Well, don't be afraid, it looks complicated, but it is not. The whole idea is that if we don't have enough time to put all those special quality assurance techniques, tools, different stuff which can increase the quality of our product to every single part of our software, we don't have enough time, we don't have enough resources. We can use defect prediction, we can use this result of our work with artificial intelligence as a kind of decision point. If the particular module was predicted as a defect prone by the artificial intelligence, let's put everything what we have regarding the quality assurance in this module. But if it was predicted as a non-defect prone, non-dangerous, let's say, or non-risky, okay, so maybe we should only fix some bugs inside, some defects, and then leave it as it is. And after implementing, after introducing KNIME/DPRESS in the projects, and after introducing defect prediction-driven quality assurance methodology, once again, I have no idea why all those letters are cut. We started to observe the potential results for using this approach. And after I did some business cases, some modeling, some simulations, well, it turns on that we can easily decrease total quality assurance costs by using artificial intelligence and this approach. And also, after we observed together with a different software development teams, total costs of implementing these solutions. As you can see here, the longest time was spent on training, because to train people how to use DPRESS, how to use KNIME, we had to spend entire 4 hours to show them how to use KNIME. If some of you was on one of my KNIME workshops, you know that this workshop takes 4 hours, and after that you know how to use KNIME. But after that you need to, every single time you need defect prediction, you need to spend 3 hours to collect data. Of course, you don't collect the data manually. You should use some different tools, but still it takes roughly 3 hours to do such. But still, compared to this decrease of quality assurance costs, after some magical calculation, well, the return on investment from using artificial intelligence, from using KNIME tool to increase quality and decrease quality assurance costs, it turns out that this return on investment is 7,300% in the best case. So even if it's just a fraction of this value, it is still a good result. But that's not the end, really, because that's the result of using artificial intelligence in a projects from a cost perspective. What about quality perspective? Maybe some of you already know from the I don't know, from some of my publications of presentation, this chart. We also observed that by using this approach, we can easily reduce bugs. We can not bugs, defects in a in a software. This chart illustrates well, defects found on the production environment in one of the software we were well, developing, this time without the artificial intelligence, without the defect prediction. And after we started to use this approach, that happened. As you can see, we didn't observe any of high priority defects during the entire lifetime of the application, which is 1 year, and starting from September, we didn't observe any defects at all. And after such results, we thought, especially I personally thought, that everyone will be amazed with those results and everyone will start to use NIME, machine learning, artificial intelligence to predict defect-prone areas in the software. Maybe not as a main tool, maybe not as the most important basis of the quality assurance process planning, but at least as a kind of support, just to know what, according to the artificial intelligence, will be the most risky part of the software in the future or in the new release. And unfortunately, in most cases, reaction was such. Of course, me and my friends in the different companies we work for, because still I'm telling you about my research team from the technical university. We presented this idea to different teams, to different companies, and in most cases, that was the reaction. Of course, the idea is tremendous, is very, very promising, and we will start to use it someday. Maybe never, but because we don't have time for that 4 hours of training and 3 hours of collecting data. And in the beginning, I personally thought that the actual reason which is behind this reaction is a kind of teddy bear reasoning. Well-known to all of you who like the old Polish comedy movies, teddy bear is I guess the one of the well-known movies. But in the teddy bear movie, we can find such well, such quotes, such dialogue or monologue. Nevertheless, if no one knows why we have such teddy bear, then no one will ask about it. And same with defects or defect-prone areas in the software. If no one knows where should we expect most of the defects, where are those most defect-prone areas, then no one will ask questions, just simply, about those areas. So initially I thought that that was the main reason. And we should somehow change the approach and present this technique from a different perspective. But as long I was working with different teams, we were working with different teams, we tried to convince people to use this technique, we started to observe such reactions. For example, here you can see an email from a well-known person from an artificial intelligence / quality assurance world. Maybe well-known person to most of you, from 2013. And this email was sent to me by mistake. I was presenting the idea of the software defect prediction to their team, as a new idea, as an innovative idea and a very cheap idea based on the open source free software. But by mistake, they revealed the actual reason why they don't want to cooperate. Because as you suspect, the answer for this email was the second. I prefer to get rid of this guy because, well, we don't have time for that, you know. Another tool, another thing to learn, another 4 hours of training, another 3 hours of collecting data. Maybe, of course, maybe it will give us better picture of the quality of in the future releases of our software, but another hours of another tool, no. Okay, so I thought then, after that, that this is the bottleneck for spreading the news, for spreading the actual usage of this technique, that those 8 hours of total work, which is, or workload, which is required in most cases to start using artificial intelligence for the defect prediction, it's still too much. And, yep? Mm-hmm. Oh, okay, I got the idea. So the question was why we have training here, because in some cases people actually know how to predict defect-prone areas, maybe from their experience, for example, or using different tools. Well, first of all, this particular table is just simply cut and pasted from my paper, from my publication. So that's why we have this cost here, and this cost have some variables here, unknown values, because I cannot share the actual budget with a world, right? Yeah, and we can still calculate this. I can point you to an entire paper when the step-by-step this calculation is explained, and everything will be crystal clear. But regarding your initial question, why we have training here? This is mostly the tool training. So we are starting with a person who don't know machine learning, artificial intelligence at all, and don't know NIME tool at all. And as NIME as a tool was created in the University of Constance in Germany, mostly to be used in medicine, with medicine doctors, because they are not, in most cases, technical people. They don't have technical background, but they still have a plenty of different data to be analyzed for their purposes, right? So the NIME was created to allow such people very easily to use artificial intelligence, to use machine learning for the prediction purposes, for example. So for technical people, like software developers, like testers, in most cases, it takes 4 hours. From the tabula rasa to a person who can use it for the defect prediction purposes. Maybe not NIME master, but to use it for a defect prediction. Yeah, but still, I thought that if this training, for example, if this data collection, it's a bottleneck, then maybe we should automate with 3 exclamation marks the entire process. And maybe we should create, maybe I should create, or I should hire or include in the team someone who will also help me with that, some kind of server which will collect all the data needed for the machine learning, for the artificial intelligence, and then the server will be able to pass the result of the defect prediction to team members or different teams. Maybe that's a good idea. Yes. Okay, the question is what NIME tool does. Once again, this particular presentation is not about defect prediction basis, and you are asking about the defect prediction basis. So I can explain you in details after the presentation. Is that okay? Okay. But this presentation is about fully automating the artificial intelligence usage in the quality assurance. And the idea was to have such central located server which will do all the work for us, collect all the data, interpret it, do the machine learning, and then pass it to users. And once again, this data collection was the bottleneck, was the most difficult point for the entire process. But a tool exists, a free tool, open source tool, which can easily collect data from a different software development projects, very useful data, and tool is called SonarQube, previously Sonar. And maybe even if the SonarQube itself provides fancy looking charts or some calculations or some values to end users, under the hood, inside, in the interior of SonarQube, we can find a plenty of different data which is even more useful for the artificial intelligence than this data which is presented in this fancy look on the SonarQube front end. So the final idea was to use SonarQube for collecting code metrics, to use different code repositories like SVN, Team Foundation server, Git, to collect code changes, why code changes. I will tell 2 sentences later after that. And defect information from a defect tracker software. And then do some artificial intelligence magic on all this data and pass it using JSONs to our team members, our teams. And once again, it's not a task I can do by myself, especially when I was strongly involved in creation of different PowerPoints for different organizations and companies. And that's how Offchar appeared. Offchar, woo! in the team. And together, mostly with Offchar's hands, we created Adept, automated defect prediction system. And this last part of this presentation will be recipe for you, will be kind of, I don't know, instruction how to create your own Adept, your own automated defect prediction in your own teams, in your own companies. So do it yourself. Now the technical stuff is going to happen. Okay, this looks very complicated, but it isn't, really. Here we have a different, this presentation will be available online, so don't worry. And also those charts will be, or already are available in some of publications, some publications. Here we have different data sources. Some of those data sources, some of those tools have API interfaces, which can be used for a communication with our Adept, automated defect prediction. And you also can use APIs to get data. And what kind of data you need to have AI-driven defect prediction in your projects? First of all, you need code changes, source code changes. Why you need source code changes? Because you need to distinguish among all the source code changes, only those source code changes which were done as a result of defect fixing. If you have it, if you have them observed, then you can easily observe all those parts of the software which were most defective in the past. Why in the past? Because here you are creating training data set for our artificial intelligence. We train our machine. We do the first phase of the machine learning process. And after collecting our code changes or via API or, well, for example, in a simple form of generating a changelog, we combine this all code changes with a defect information which came from a defect tracker, and as a result we recognize those defect fix induced changes among other. And after that, if we add this SonarQube sources data, code metrics, we will have training data set. Once again, if you want to know details, there are plenty of different stuff and YouTube videos available. Also, we can talk about this later after this presentation. Yeah, but what about the second phase of the machine learning, the new prediction for our software? Then, of course, we also have to know if this release of the software is the new release for which we want to have prediction, because we don't have any defect-related information, because we even not started to test this new release. So you still need to integrate your automated defect prediction system with code repository, but you already did it here. So this one is covered. And then once again, you need new code metrics, once again from SonarQube API, to have your new metrics data set. And then if you have your training data set, you can do all the machine learning magic in the Adept, in the server. It depends on you what kind of magic you will use. But I strongly recommend to use this feedback loop in the process. When you will create prediction model after machine learning phase, then you can test this prediction model against the actual knowledge about the defects in your software. For example, using historical information from the software, and check the result of the prediction. If the prediction is good enough, then of course you can leave it as is. If not, you can change the parameters of this machine learning and then repeat the process. Like, for example, here, what is going on with this? I have no idea. Nevertheless, look here. We are starting our we have our historical data. We are splitting this data in two. We are using half of the data in a machine learning process, and half of the data as a kind of testing data for this classifier, for this prediction. And then we compare the actual defects with the actual defect-prone areas with the areas which were predicted as a defect-prone. And is such easy way we can assess the efficiency of our defect prediction. What kind of classifier we can use? Simply saying what kind of machine learning mechanism we can use. Of course, together with Ovchar here, we tested, well, Ovchar mostly tested many different classifiers. But at the end, I found such paper when a nice chap called Fernandez Delgado with his friends tested 179 different machine learning algorithms. And the conclusion of the research question from this paper, do we need hundreds of classifiers? Do we need hundreds of machine learning stuff to solve real-world classification problems, like, for example, defect prediction? The answer to this question is no, we don't need. We only need one classifier, which is called random forest. End of story. And our personal results from this automated defect prediction implementation also confirmed this fact that random forest classifier is the most efficient classifier for such application. And going to the end of my presentation, once again, what we did, what mostly Ovchar did, was not writing something from scratch, creating all those algorithms, creating all those classifiers. No, it was very similar to those connecting different blocks together from NIME tool, just in Python. As you can see, we already have different models, different bricks in Python. The only thing which you need to do is combine them together, implementing this recipe I presented to you. And then, as a result, you will have working automated artificial intelligence for the sake of defect prediction in your projects. Also, 2 words about the presentation for the users. Very simple. For example, we were using an integrated development environment plugin, which will, after opening the source code, which were predicted as a defect-prone source code file, was indicated this fact with just nice-looking red bar with statement, this file contains, yes, I hear. Or, what also created Ovchar was this subtle red triangle next to predicted classes. We also created a special interface for testers when we were able to translate the raw prediction results to actual functionalities, and then testers were able to put a special test cases, prioritization, and so on those functionalities. This is how the tool looks like. And the conclusion, I have no idea what's going on, of this long story is, of course, we observed a dramatical increase of using our software defect prediction techniques in different projects, in different companies. We also observed a nice decrease of number of defects before using artificial intelligence and after. But also there were many cases when such red bars, for example, were just simply ignored. And people, even if they had the result of the artificial intelligence based analysis delivered to their own computers and the only thing which they had to do was to react to those results, they still just simply ignore this message. And 2 sentences, how we learned, for example, that those messages, this presentation was ignored after the main server, the Adept automated defect prediction server, just simply stopped to work after some network problems and so on. And then this plugin, which shows this nice-looking red bar, started to display a very ugly message saying that there is no connection with the server. And only one person among different projects contacted us saying, guys, do something about it, because I had this strange message on the screen. Why those people contacted other people did not contact us? Because they switched off the entire process and the entire mechanism. And with this nice looking Hanna Hala approved message, I want to thank you for listening to my too long speech about the automating defect prediction, whatever stuff. And if you will have any additional questions, you know how to find us, Ovchar and my helpful person. Thank you once again.
Okay. So thanks a lot.